So it's very nice to be able to introduce Rajaram to give a lecture today about logarithms. And Rajaram, pretty much everyone knows Rajaram here. He was the director at NCRA, and before that he was at RRI, and now he's at ICER. I know Rajaram actually from before I came to IUCA, because I was teaching at a place near here. And I knew him not as Rajaram, but as Usha's husband, because I was teaching with her. And I knew he was a professor in astrophysics, but because he's so down to earth, I never realized how famous he is in the community until later, until I came to IUCA. And so if you look on Wikipedia, you'll find that it lists his research areas as astronomical optics, image processing, and gravitational dynamics. But if you look on ADS, I think he's kind of a modern Renaissance man, because he's done research in so many different areas. I'll just list a few quickly: condensed matter physics, telescope mirrors, black hole evaporation, accretion disks, gravitational lensing, observational techniques, dynamics of stellar systems, GR, and most recently the Chandrasekhar limit for white dwarfs and quantum plasmas. So it's pretty astonishing how broad his interests are, and what he's probably most famous for, and why maybe the main reason why we invited him as students and postdocs today, is he's most famous for his teaching and his ability to just give completely impromptu lectures, whether it be on the physics of swimming or some other topic, or if the speaker didn't show up, and he's the one to go to give a lecture without any preparation at all. So without further ado, let's have Rajaram.
Inconveniences were available. It's a pleasure to be back. The overall context of this talk is something which people involved in astrophysics are very familiar with, namely order of magnitude estimation and dimensional analysis, but a particular corner of that. So before I plunge into this corner of scaling and dimensional analysis, I can't resist quoting V.I. Arnold, who in one of his books, he's a mathematician and therefore enjoyed poking fun at mathematicians, and he said there is something called the axiomatic method, which has the advantages of stealing over honest work. Okay, that is, Pythagoras had to work to prove his theorem, but today a Euclidean structure is defined as something which obeys Pythagoras' theorem. So I think the same can be said of dimensional analysis and order of magnitude estimation. It has the advantages of stealing over honest work, which is why some of us love it so much. Now, astrophysicists also have this tremendous faith that if something depends on something else, it must be a power law. I mean, the observational people plot a log versus a log and they get a slope, but even the theorists like to look for power laws, and these two techniques, if you're lucky enough, the quantity that you're interested in depends on not too many other quantities, then dimensional analysis will lead you to power laws. Now, this talk is concerned about some special cases where that power turns out to be 0, as is indicated in the title, which means you would think, if y is x to the 0, then y doesn't depend on x. But then you have sound reasons to believe that y depends on x. So what happens? So nature's answer to this problem is to use the logarithm. Okay? I mean, in a very naive mathematical sense, a logarithm is the closest you can be to x to the power of 0 without actually being constant. So let me give you an argument for that, which will not be rigorous, of course, obviously. So if you take x to the n and you integrate it, you get x to the n plus 1. Okay? So if you want n plus 1 to be 0, you can choose n equal to minus 1. So if you integrate 1 over x, you don't get a constant, but you get a logarithm. Okay, So we have to now start with a specific problem. And to start off with, I've chosen the problem of a body moving through a fluid and finding out the drag on it. And this is a very venerable problem. Newton himself worked on it. Okay? And he actually, of course, had some elegant mathematical theory, but in the spirit of order of magnitude estimation, you have this object whose size is, say, L. Okay? And there is a fluid of density rho, and you are trying to move this object at some speed v. So let's instead say that the fluid is coming and flowing past the object at this speed v, all right? And your idea is to find out what this drag force is, pushing it this way, okay? Well, this is one of those fortunate cases where, you know, there'll be only one combination of these three quantities which will have the correct dimensions of force. Okay? So here's the famous Twiddly sign, which means that I can have 64 pi to the 4 here, but I'm not going to worry about it. I mean, I do know one case where you actually get 64 pi to the 4, but anyway, so you have rho times v squared times L squared. Or this is an area, but this is pure dimensional analysis, but one can also do order of magnitude. One can say that 1 rho v is the mass current, mass hitting unit area per unit time. If you multiply it by 1 more v, it's the momentum hitting unit area per unit time, and then you multiply by the area, then you get the total momentum transferred per unit time. Of course, that's order of magnitude. Deeper physics, you have to ask what happens to this fluid after it hits this. You know, in an extreme case of an ideal fluid and a very nice body, the fluid just flows around and comes out with the same momentum. So, you know, we're not worrying about cases like that. So here is our formula for the drag. Okay? Now, this is a standard case of dimensional analysis. So let's use this to calculate the optimum depth of a swimming pool. And I don't mean the Ayuka swimming pool where diving is prohibited. I mean a swimming pool where you're allowed to dive into the swimming pool. Okay? Right? So now you have to, and many places have a 3-meter board, a 5-meter board, a 10-meter board, a 15-meter board. And if you jump off those, you can check that using the same formula that the air resistance is not going to slow you down very much. Okay? So you will attain a value of v squared when you enter the water, which is proportional to the height. Now what happens after that? So let's approximate the diver by something of cross-sectional area A and length L. Okay? So the mass of the diver is going to be the density of the diver times the volume, right? And if I multiply this by half the initial velocity squared, this is the amount of kinetic energy that you've got to get rid of, right? So how deep should the pool be? Okay. So again, in the spirit of order of magnitude, this is the depth of the pool, and let's multiply it by this drag force. Okay? So the drag force will now be the density of the fluid times this area of cross section of this diver, and we also set v squared. Now, of course, one has to be a little careful. Do you put v initial squared, right? All right. Let's just put some v squared, which is proportional to v initial. Okay. So then you encounter our first zero power, right? So let's see. This is the depth of the swimming pool, which what you want. Now you may say, by the way, the density of the diver is practically the density of the fluid. Otherwise, we wouldn't be able to float in water. Okay? So I'm quite happy to cancel off these two terms. We cancel off the area, and Anyway, things like half don't make difference when you have this wiggly sign. So you reach this interesting conclusion that D is of the order of L. So swimming pools, regardless of how high the diver dives into it, should be made of a length of the order of the height of a person. 5 feet, okay, you want to be safe, 10 feet. Now, interestingly, swimming pools are made that way. Okay? Rarely you will find a swimming pool which is 20 feet deep. Right? And so there's some truth in this. However, it can't be the whole truth for the following reason. So let's say the diver travels a distance L. Surely the speed has not come to 0, right? It has some speed, but since speed cancelled in this equation, you can use that to show that the diver can again go by a distance L at whatever speed he or she happens to be after traveling a distance L. Okay? So now what? You get a kind of series which is L plus L plus L. But in reality, of course, the velocity goes down with every L by some factor. Let's say half. Okay? So, so suppose you have a V final, which is a V initial into 2 raised to minus n. Okay? So after n steps of this. So then the depth of the pool should be chosen as n times L, which is L times the logarithm of V initial divided by V. So here's our logarithm, right? So we did it naively and concluded that the depth of the swimming pool is independent of velocity. But when one used a slightly more sophisticated argument, then one concluded that, first of all, there's a new scale which appears, right? We initially said we want the depth of the swimming pool as a function of the initial velocity. But it turns out now it also depends on the final velocity, okay? Which we had not really thought of. Now, in practical terms, you don't have to worry. Okay? Now, I'm basically a theorist, and I cannot claim to have verified this equation. I did try in the Indian Institute of Science long ago, but the problem was even at this stage, because I was something like this. So anyway, so therefore, then you only travel this distance, right, which is rather small, and you also never go for a dive again. Okay? Now, of course, there's a better way of getting this logarithm. Even a nicer way of writing this equation would be dv square by dx, right? The rate of decrease of kinetic energy is minus some constant into v square. Right? So this is the way the logarithm really comes. The logarithmic dependence of x on v. But now, I actually gave a version of this talk to my former colleagues in TIFR Hyderabad, and I had to apologize because, that this is not a cutting edge talk. So I said, this will not be rocket science, but I can tell you about these things. But curiously, there is a little bit of rocket science which is connected with another logarithm, okay? And in some ways, it's perhaps similar to this. So the way rockets work is that they burn this fuel, which becomes very hot, and then it's put in a rocket engine. And the theoretical physicist version of a rocket engine is a spherical cavity in which you have this hot thing, and you make a hole on one side. So all the hot gas goes out in that direction, and the rocket gets pushed in the opposite direction. So clearly, the speed of the rocket is going to depend on the speed of this exhaust, which is going to depend on the chemistry of this fuel. So in fact, it's a nice exercise, simple exercise, which I even assign to my students in ICER to take, the binding energy of H2 and O2, 2H2 and O2, which is some 6 electron volts, and convert it to kinetic energy. What kind of speed will you get? You get about 5 kilometers per second. Okay, so you have a V exhaust, okay, which is of the order of 5 kilometers per second. But this is not enough. Okay, I mean, you might want to escape from the Earth. So that means 11 kilometers per second. So what's the velocity of this rocket as a function of this exhaust speed? Okay. So again, we will encounter a dimensionless number, So again at this, now I think many of you may know that space missions are really very small payload with a huge amount of fuel. Okay? So let's take the mass of this payload to be 1, and let us have some 1, 2, 3, n pieces of fuel, okay? Or maybe n plus 1 if you don't mind. So then we can idealize the thing in the following way, that first this much fuel is burnt up and shoots off at a speed equal to V exhaust. Now, based on that, because the mass ratio is 1:n, I think, the rocket in the original frame picks up V exhaust divided by n. Now, of course, it's got a bit lighter, so when it throws out the next one, it picks up V exhaust by n minus 1. So finally, you get V exhaust into 1, well, whether you have the 1 or not doesn't matter, 1 plus half plus 1/3. So the nice thing is that this is a divergent series, okay? That's nice because you can attain whatever speed you want, that's the good news, okay? By choosing n large enough. The bad news is that it's a very slowly divergent series. So this is not terribly different from integral of dx over x, right? With which we started, 1, 2, 3, 4. So let's say this is 1, this is 1, this is half, this is 1/3. Practically the same as this. In Tamil Nadu, we'll say there's a little kosuru here, and in I think North India, you will call it pav, a little bit of extra. So really this series is log n plus this extra thing which is called Euler's constant. Anyway, apart from that, you basically see that n is the ratio of the initial mass of the whole thing, payload plus fuel, to the mass of the payload. So you get this famous equation, V final equals V exhaust into logarithm of m initial by m final. Now this is catastrophic actually, right? So you want to put 500 kilograms somewhere and get it up to 11 kilometers per second, and you can see that getting a good value of V exhaust makes a huge difference because, by the way, this talk, instead of being called logarithms, could have also been called exponentials if I had read all the equations the other way. And maybe that is the way to read this equation. So m initial equals m final exponential of V final over V exhaust. So that's the tremendous importance of getting the right cryogenic engine and so on to get get a large value of this. I mean, you put in numbers and then you realize that, the weight you hear for the Saturn V's or PSLVs as compared to the final payload is quite reasonable. Okay, so this is the rocket science logarithm. This logarithm is probably quite elementary, but if we want to name each one of our logarithms, this one probably should be called, this one should be named after this person. Okay, now let's get back to this body which is being dragged through a fluid. In order to make life simple, one took it to depend on 3 quantities, and this is what Newton did. But the same Newton also gave you a law for viscosity, okay, which is a different kind of force which you get when layers of fluid slide over each other, right? So viscosity is a force by an area, force per unit area, which goes, this is viscosity, right, which goes as, the force per unit area goes as the viscosity into a velocity gradient, okay. So if someone had told you that construct a formula for the drag force given viscosity and the size of the body and forgotten all about the density of the fluid, okay, then you could have constructed a nice formula, right? Just move the area up. So F, I'll just call this Stokes, because it goes dimensionally at least as eta into V into some length. Now, we have two formulae for drag. In one of them, you have conveniently ignored density. In the other one, you have conveniently ignored viscosity. So which formula should one use in a given situation? So as a person who has held administrative positions, as you heard in the introduction, I can give you a very simple answer. This is given by Murphy's law. Okay? So the drag is really the force, what you have to pay in order to keep moving at a velocity v. So any good administrator will tell you that you calculate both, and whichever is higher, pay that. Okay? So let's see which is higher. Okay? So we have rho times v squared times L squared divided by eta times v times L. So what does that become? It becomes rho times v times L by eta. And this being the ratio of two forces is dimensionless. Okay? So if this quantity is large, which means you have big bodies moving at high speed through a fluid which is not very viscous, right? This is the famous Reynolds number. Then you use that formula. And certainly, if you're talking of aeroplanes and so on, more or less that's the formula you should use. I mean, obviously better versions of it. But the Stokes regime is where you're dealing with very small objects moving very, very slowly. Now, putting in some numbers, this eta, if in CGS units, one good argument for CGS units is that the density of water is 1. So I can ignore that. And eta is around 0.01 for water, though it depends strongly on temperature. So when V times L is of the order of 0.01 centimeters square per second, that's when you should start using this formula. So you say, who is interested in anything which is this slow, right? Very tiny objects. Turns out that biologists are very interested because, bacteria have to move around. And, bacteria are not some things out there, right? All of you probably know that there are more bacterial cells in our own body than our own cells. And all these guys are doing useful work for us most of the time. So in this extreme regime, which is called the Stokes regime, right, you use this formula. No logarithm so far, okay? However, there's something called Stokes paradox. As you've all seen the famous formula, 6 pi r a eta v for the drag on a sphere. But Stokes said, okay, why not? Any decent theoretical physicist will solve something in 1 dimension, 2 dimension, 3 dimension, all the way up to 26, right? So let's say you have a cylinder. What would be the drag per unit length on this cylinder, okay? Drag per unit length of the cylinder in the Stokes limit at a very small Reynolds number. So very simple, just knock off this L, right? So it's eta into V. So what's the dependence on the radius of the cylinder? 0, right? No dependence on the radius of the cylinder. Okay. Now this is called Stokes paradox because he was unhappy with it. And I mean, being a good mathematical physicist, he also had other reasons to be unhappy with it. When he solved the problem outside a sphere, far away the velocity would be the uniform velocity, and then there's a correction term, which keeps increasing as you approach the sphere. And that correction term goes as 1 over r, okay, which is fine. You're solving something like Laplace equation, some much more complicated equation, but anyway. But when he has solved the same thing in 2 dimensions, it went as log r being the radius. Now log r has this interesting property. Of all power laws, it's the only one which behaves badly at both small r and large r. Okay? Any other power, greater than 0, fine, behaves nice at small r. Less than 0 behaves nicely at large r. So, if you're left with a log r solution, what do you? Okay, at the cylinder, you'll be fine because you don't have to go to r equal to 0. But then when you keep moving, you're not able to reach infinity, right? So this Stokes paradox, it was around for quite a while, okay? And it was resolved only very much in the 20th century. And the answer is interesting. And in fact, it's a kind of 20th century answer in some sense. So one made an approximation, right, that one neglects. So these forces are called inertial forces, right, rho v squared kind of forces. Because they depend on the inertia, the momentum coming and hitting this. And these are viscous forces. And we just had one Reynolds number which told you which was more important. Okay? However, one could argue as follows. This is a non-mathematical argument. So this is our cylinder. Right? Now this viscous force, so okay, let's say the fluid is coming like this. So there is someone else is holding this in this position. Okay. So this force is of course transferred to the fluid, right? I mean, you're pushing this and it gets transferred to the fluid. So you have to look at different scales. And what you find is, if you take this velocity perturbation variation log r, I'll spare you the details, then you find that this ratio of these two terms actually depends on r. So instead of thinking of Reynolds number as a number characterizing the flow, that was the naive interpretation. In this cylindrical geometry, what you find is the Reynolds number increases as log r. So something, and therefore at some point you will get to a place where this approximation is no longer valid. So then after that you use some other solution. And I mean, what I've given you is a very qualitative argument, but I mean the mathematical tools for doing this were developed in the field of fluid dynamics. It goes by the name of matched asymptotic expansions. It's a learned name for saying you have some approximation which is valid somewhere, some other approximation is valid somewhere else. Try to find a region of overlap and match the two. Okay? So the lesson for us is Reynolds number, which we thought was just a number, is actually scale dependent. Now, I don't want to get completely out of my depth into particle physics, but even reading particle physics from physics today, you will realize that something similar happened in the 20th century to quantities like the charge on the electron, what you call coupling constants. Yeah? So when I did my MSc, coupling constants were constant. But gradually after that, coupling constants started to become dependent on scale, dependent on energy. They started to walk instead of just sitting there. Okay? And interestingly, that walking also takes place logarithmically. Okay? But I will not, having dipped my feet into 20th century particle physics, let me take it out again. But you will see these logarithms ubiquitously if you, but actually there is a moral for particle physics. It really tells you that you can't have it both ways. Either things will behave badly at small distances or they'll behave badly at large distances. Now, history is that people like Landau looked at the first quantum field theory, quantum electrodynamics, and they found that actually the first papers were not even Landau, it was Gell-Mann and Low and others, that there is something going wrong at very short distances. And Landau drew a strong conclusion that therefore I'm going to give up field theory. He gave it up is fine, but he also prevented his students from studying field theory. So some of them had to study it seriously. I read a blog by some of them, and they admire Landau, but they still feel they lost a couple of years because of his strong. So the solution found by people was to find other field theories, right? And which are badly behaved at short distances. Anyway, that's an excursion. Okay. So let's get back. So we've talked of Stokes paradox, okay? And basically the drag goes as the logarithm of 1 over the Reynolds number. Reynolds number is small, so the drag on a cylinder. So it does depend on the radius, okay? But depends in a somewhat unexpected way. Okay. So let me move to the next logarithm, and I'll call it the NCRA logarithm. And the reason is simple. If you look at the two major telescopes built by the group which is going to celebrate its 50th year shortly at the end of this year, there's the UTI radio telescope and there's the GMRT. Now, both these telescopes are based on this very nice idea, and whenever visitors come, we explain it to them as if it's very obvious. So you go to the UTI radio telescope, we say, okay, there are 1100 wires. They are all spaced just few, I think about 2 centimeters apart, maybe 3. And the wavelength is 90 centimeters. So how can it get through? Okay. So it reflects. Same thing with GMRT. You have this mesh. But suppose one thinks about it a little more. Then the first problem you would like to understand before understanding a large number of wires is to understand one wire. Okay. So here is a wire of radius A. And again, by now you would have guessed that you run into these logarithms when you work in cylindrical geometry, when you work in 2 dimensions. But first let's look at 3 dimensions. So suppose you had a small metal sphere of size A, and electromagnetic waves fell on this sphere, and some of them get scattered. So this is a problem which is often handled in quantum mechanics courses. Of course, not usually handled for electromagnetic waves, it's handled for Schrodinger waves. But basically what happens is, at very long wavelengths, which in quantum mechanics would be low energies of the incoming particle, you get a cross section which simply goes as A square. Now actually there's some interesting physics as to why it's not pi A square but 2 pi A square and so on. But the spirit of this lecture is not to worry about 2's or pi's. Okay? Goes as A square, actually becomes independent of the wavelength. Now if that was true, then we'd be in deep trouble, right? Then you would say the cross section per unit length of this wire, well, what else do we have? We can put in A, okay? But that, first of all, we told all these visitors that the wavelength is very long, but the wavelength is not appearing in this formula, okay? And the second thing is, these things are transparent. Occasionally, one has taken visitors who look at the GMRT antenna and say, fine, but where's the antenna, right? Where's the reflecting surface? And then you sort of take them close and say. So these are geometrically thin. The amount of area blocked by A is a rather small fraction. So clearly the cross section must be much more than A. So okay, great. So why not say the cross section is lambda, right? So that's fine. Except now it's independent of A. Okay? So even if you shrink the wire to 0, that is, those of you who know Professor Govind Swarup knows that he believes in strict economy. Okay? So if this was really true, then of course he would have made the wires much thinner than they are. Okay? So on the one hand, we would like the wavelength to come in. Okay? So we put a lambda, right? The cross section should increase with wavelength, but we also want it to go to 0 as A goes to 0. Now how do you do that? So to cut a slightly long story short, the way it happens is that the cross section per unit length, which itself has to be a length, is lambda divided by logarithm of lambda by A with some factors. Usually logarithms are of the order of 1, 2, 3, something like that. But certainly in the case of the UTI radio telescope, this is less than a millimeter and this is 90 centimeters. So this logarithm is significant. Okay? Now I'd like to say a little more about, I'm just saying that you get a logarithm here, but why? Okay? So in this one case, let me go a little more into the physics, into some kind of order of magnitude estimation. The physical picture is that the electromagnetic wave comes, drives some currents in this wire, and those currents radiate. Okay? So if you have some current flowing in this wire, well, what we know from low frequencies is that this current will produce a magnetic field like this. It will produce a B going as 1 over R. A B in this direction, which means you can have a vector potential in this direction going as log R. So that when you take a differentiate this vector potential, take its curl, you end up with this B. By the way, this is not electromagnetic theory. This is just static currents. But once you have an A and it varies with time, you are definitely going to get a E, dA dt, which will be this log R. Okay? So in zeroth order, you have some currents, and you don't expect currents to produce an electric field like this, but they do. Once you include the d by dt brings out an omega. Okay? So of course, at zero frequency, it doesn't happen. So E goes as omega log. So that's the E produced by this current. Now that E is actually very useful because ultimately there's a boundary condition on the walls of the cylinder, right? You have to satisfy the condition that the electric field vanishes here. Now the incident electromagnetic wave, suppose we didn't have any wire, right? And we were in cylindrical geometry, then you would want a solution of a wave equation which was well behaved at the origin, and that's this one, which goes by the name of J naught. But J naught really describes the situation when there is no wire. Okay? Waves come in and go out. That's it. If you want to put a wire, you have to satisfy a condition that you're zero at some radius. I mean, this is the physics. I'm now giving you a little glimpse of the mathematics. Okay? So of course, this has another solution which no one ever tells you about, which goes like this, and which behaves as log of x. And I think, if you like, this is the physics of that log of x. Right? Now, of course, we have to give this some name. So this is what it's called. I mean, if you ask why this name, then my answer will be why not. Okay? All right. So, by the way, this is not the whole story of why a mesh of wires reflects. This tells you how one wire behaves. Then you have this nice exercise of the field scattered from each wire goes and affects the other wires. So it's a very nice problem, but not in the spirit of this lecture. When you do all that, you actually get formulae, which were of course naturally used, which have been known for many years, which were used in the design of these meshes, which have driven these two telescopes. And of course, in some ways, this might be my favorite logarithm because it involves electromagnetic theory, and it paid my salary for 13 years. Okay, right. It's somewhat similar in spirit to the previous one. In the sense, it again has to do with potentials in 2 dimensions, and so on. Okay, and this, I mean, the title said some that I have known. Well, these are some that I have learned, but sometimes you actually encounter it in your own research work. And this has to do with gravitational lensing, which very simple-minded approach is that you have some mass here, and you have a plane wave coming from far away. Okay, and we're not going to worry about diffraction or anything. So even if you're not worrying about diffraction, it's still nice to think of this family of rays as perpendicular to some wavefront. That's a useful way of looking at it. So instead of saying that this gets deflected, right? This is the famous formula for the deflection, which is so B is this impact parameter. Okay. So a ray passes this mass at a distance b and gets deflected by an amount which is dimensionless, which is the ratio of the Schwarzschild radius associated with this mass to the impact parameter. Okay? I mean, this tilde, of course, conceals a lot of interesting things. A formula like this was worked out in 1801, and it had a factor of 2 here, I think. And then Einstein redid it in 1908. He also got a factor of 2. Okay? And then people went out to test this formula. Fortunately, all those experiments failed because of political conditions in Russia, clouds, etc., and during eclipses. So finally, when the experiment was done, Einstein had got his act together and converted this 2 into a 4. Okay? And fortunately, the experiment verified 4. so even Einsteins need a bit of luck. But now, coming back to this wavefront, okay, it's clear that if these rays are tilted in this way and they remain perpendicular to wavefronts, that's a very sacred principle which even general relativity cannot overthrow. Then one can work out the shape of this wavefront, right? If you call this y and call this x, then dy by dx is proportional to 1 by x, right? The deflection. Dy by dx is the slope. I mean, the slope of this with respect to the x-axis is the same as slope of this with respect to the y-axis. So y goes as log x. So now we get a formula for what you call the gravitational time delay or path delay. The path delay would go as gm over c squared log of b. In the time delay, put an extra c. So it's a nice formula for the time delay, and it's useful. Right? However, it has a problem. What does it do at large b? Okay. By the way, I should relate one interesting experience I had. I was lecturing in a summer school in quite an interesting place, Iran. If you wonder how I got to Iran, the answer is very simple. Jayant sent me. Maybe someone in the IIU asked him, we are conducting a school in Iran. He said, send this man. So I went there, and there were, of course, people from other places, including Maryland and so on. So I wrote this equation. And then I had, this is one of those pleasant moments where a hand went up from the back, not from the students, but from this other lecturer. He said, you can't do this. How can you put a dimensional quantity inside a logarithm? I said, okay, I'll put something, some L here, and then I will use the properties of logarithm to write it as log b minus log L, and this is a constant, so I don't care. Okay? So this is the other interesting property of logarithms. You can actually, the formula makes sense. I mean, exponential of a dimensional quantity would get you into deep trouble, but logarithm of a dimensional quantity is curable by finding some other scale. But there is actually a genuine problem here, which most of us who work in gravitational lensing don't worry about. Right? What happens to this at large b? Right? How do you match it to a plane wavefront at large b? And there are interesting answers to that. I think one of the themes I mentioned is that when you encounter these zero power problems, they force you to look at some other scale which you had not looked at before. Okay? So in this case, one of the ways of making it is, say, the source is not at infinity. So let's say the source is here, all right? So if the ray passes very close, you get this full deflection. But suppose b becomes greater than this L, the distance of the source. I'm sorry, I'm calling all lengths L. No? It's not very good. So this is d. Now suppose b becomes greater than d, then what happens? Then interestingly, you still get half the deflection. Right? I mean, earlier we had a full trajectory from minus infinity to plus infinity, which got deflected by this amount. You still get half the deflection, so that does not solve the problem. And actually, I think it's a somewhat deep problem. And again, getting a little bit out of my depth, I've read one paper by Raphael Sorkin and his colleagues who have used this notion of gravitational time delay in general relativity to say something about the asymptotic structure. And they used it as an alternative proof of something called the positive mass theorem. Now, the positive mass theorem is something which you need in general relativity because on the one hand, you have some nice properties which you assume for this energy momentum, which sits on the right-hand side of Einstein's equations, right? But that's a local thing. But mass is defined by the gravitational field at infinity, okay? Now, how do you connect this local thing to this property? And I think there are many clever proofs of it, and one of them is actually based on this log b. Incidentally, if you also open a quantum mechanics textbook and look at the scattering of charged particles, then you will find that the wave function at large r will not be just e to the ikr, it will have e to the ikr plus a log r. And that log r is a time delay coming for the same reasons as this. So the next logarithm that I'd like to talk to you about comes from condensed matter physics. Okay, comes from an area which, as you, I don't know if it was mentioned in the introduction, but is the topic of liquid crystals. Actually, that was my first love. For my PhD thesis, I worked on the optical properties of liquid crystals. I moved to the Raman Institute, which had a nice astrophysics group, but I used to ignore them and go and sit in the liquid crystal lab. Okay, then gradually things happened. But so I will. One doesn't have to get into highly technical details to appreciate this. So the kind of liquid crystal one is interested in is called nematic. It has long rod-like molecules, and the way the forces between it work, they all tend to line up parallel to each other. Okay? So the picture of a nematic liquid crystal. Now the word, I should explain, the word liquid is used because you can actually pour this from one bottle to another in the right temperature range, or you can drink it, except they tend to be a little slimy. Okay? It's called a crystal because its properties depend on direction. Okay? So in fact, one of the most spectacular demonstrations of this property, which dates from the late 19th century, is that if you put a drop of this liquid crystal on something, you can get sharp corners in that drop, where the orientation of this. So this preferred direction is denoted by a vector n, and this vector is called the director, right? For a good reason. Everyone has to obey n, okay? It's all parallel. By the way, calling it a vector is an abuse of notation, because each individual molecule may of course have a head and a tail, but there is no, in most liquid crystals there is no preferred orientation. Okay? So actually a double-headed arrow would be better. So the lowest energy state of this liquid crystal is when everything is parallel. But it doesn't take much energy to bend these things. And in fact, so there is a nice theory of liquid crystal elasticity, which means you're not changing the volume of the liquid crystal, but you're changing the arrangement of this director. It now becomes a vector field, okay? And there's some energy stored in that. So why would it prefer a state of higher energy? It depends on the boundary conditions. So for example, you might have two glass plates, and this glass plate might tell the liquid crystal to be oriented like this, and this glass plate might tell the liquid crystal to be oriented like this. So then the liquid crystal would have to twist. Its minimum energy state subject to these two boundary conditions would be a twisted configuration. Okay? I mention this because that was the kind of liquid crystal that I studied for my thesis, but it's also the kind of liquid crystal that exists in all LCD displays. They have these two plates, they have this twisted thing, and light goes through it, and if you apply some voltage, then the voltage sort of changes the orientation here, and then light does not go through it. Okay? So, plus color and all that. So, now twist is only one of the deformations of the liquid crystal. It's the one that requires you to think in 3 dimensions. But you would have guessed that I'm going to work in 2 dimensions. Okay? So in 2 dimensions, you have 2 kinds of deformation. This goes by the name of splay, and this goes by the name of bend, for fairly obvious reasons. And you can write down mathematical formulae for the splay. Splay, I guess most of us would guess, is divergence of n. And it's not so obvious that bend is given by some n cross curl n, but it is. So liquid crystal has energy expression. It can, this is a unit vector, by the way, just gives you some average direction. So it has, and of course, I think if there's any justice in this world, the energy should be the same whether it's placed this way or this way. Okay? So the energy is going to be proportional to the square of these quantities. So that's the overall context. So the problem which my colleague G.S. Ranganath of the Raman Research Institute Liquid Crystal Laboratory was working on and got me involved in was the problem of defects in these liquid crystals. Okay? So So this is a configuration which is often seen, again forced by some boundary conditions. So this is a kind of defect. So here the director doesn't know what to do. So more microscopically you would say in this region the liquid crystal is an ordinary liquid and the molecules point in all directions. But as you go once around, this director rotates by pi, not by 2 pi. You notice that when I've gone 90 degrees, this is only turned 45 degrees. Now this is possible because this n is a double-headed vector. So this kind of defect is called s equal to plus half. And can also have this one is called s equal to minus half because when I go by 90 degrees, this rotates by minus 45 degrees. Now these defects actually exert forces on each other. Okay? So you could easily get the force by computing the total energy in this system for one value of distance, then compute it for another value of distance and differentiate it and you will get the force. So then something interesting happens when you compute the energy, and that doesn't require any details, so I can explain it to you in the few minutes that are left. Right. So take any region, and theta varies in this region. So you have an energy per unit area which goes as some elastic constant times d theta by dx. This is again some gradient, whole squared. This is an order of magnitude sign. So that's all we really need to know. Okay. Now notice that theta, if you look at one defect like this, theta has to, because of this topology, theta has to change by 2 pi. But if you draw larger and larger circles, it has more and more distance in which to bend. So the gradient of theta essentially scales as 1 over r. Right? So if you look at the scaling of this, by the way, this is the energy density. So this scales as k by r squared. All right? But now, of course, this has to be integrated with 2 pi r dr to get the total energy in the system, logarithm. Okay? Now, the lower limit is not so much of a problem because anyway there is something happening here. So there is a lower cutoff radius. I mean the particle physics is called the ultraviolet cutoff, where the liquid crystal is no longer a liquid crystal. But there is the logarithm at large distances. So one thing is to say the sample is finite, but actually in practice what happens is that these defects occur in pairs. Okay? So this occurs, and so if you take a circuit around both of these, then the director doesn't rotate. One of them contributes half, s equal to plus half, other contributes minus half pi. So that is the way the energy remains finite. Okay? It needs a cutoff at small r, but not at large r. So now I come to the really interesting thing. Suppose I just take this picture and scale it up. So by the way, to actually find out what this configuration is would involve solving some fairly nonlinear partial differential equation which comes from minimizing this elastic energy. So in the spirit of the beginning of avoiding honest work, I am not going to do that. Right? But you have some energy. Now I am going to move everything apart and the whole pattern will scale. Okay? Okay? So all that will happen is you will have blown up the picture. Now you can ask what happens to the energy under these conditions. Okay? So it's quite interesting. Suppose I scale by lambda, then the gradient, right? The gradient of theta scales as 1 over lambda. All right? So the energy per unit area scales as lambda to the minus 2, but the area scales as lambda to the plus 2. So interestingly, as I blow up the whole system and blow up the square, the energy stored in this square does not change. So this would lead you to an interesting conclusion that I can move these two defects apart without any cost in energy, right? Which is the same phenomenon that we have been encountering throughout the last 1 hour. Something doesn't depend on something, right? But there is an ultraviolet cutoff. Okay, so let's put that in, and so we've got this ultraviolet cutoff around 2 defects or even more defects, doesn't matter. And now, so if I'm going to do an honest job of this blowing up and claim that the energy doesn't change, I should blow up this also, right? So now it is completely true that the energy doesn't change when going from this to this. However, this is not the physical situation that I'm interested in. I'm interested in situations where I change the distance between the 2 defects, but the ultraviolet cutoff remains the same. Okay? So therefore, the entire contribution to change in energy comes from this region. Now the beauty is that in this region, which is very close to this defect, I don't need the solution of this major partial differential equation. I only need to understand a single defect. So what we did in this paper is to express the force between 2 defects in terms of the properties of a single defect, and as you would expect, integrating some expression like this from here to here gave you a log of lambda, because the ratio of these 2 is lambda. So then therefore, the force between these 2 is 1 over r. Okay? So I was sort of very thrilled by this. So so in those days, it was easier to travel from Raman Institute to Indian Institute of Science. So this is really long ago. So I got onto my bicycle and went and met Professor R. Rajaraman, who understood all these things. So I said, look, I have a system with a cutoff, and then I'm computing an observable, and it's divergent, but when I put the cutoff, I get an answer which is independent of cutoff. So what's going on? He said, look, this has been going on a long time. This was computed by somebody called Jacquev, and it goes by the name of anomaly. Okay? And since Rajaraman knew Jacquev personally, he also added wiser men have now found the deeper reason for the anomaly and so on. So here is a case where the logarithm actually, so this would be called a scale anomaly. That is, either if you want the system to be truly scale symmetric, not changing, then you can't put a cutoff. And then you end up with a divergent theory. You put the cutoff, it's no longer scale invariant, but you can still compute things. Okay? And there again is my slightly tangential encounter with particle physics. So the energy basically of defects is logarithmic as you move them apart. And I think you've seen enough logarithms for one evening. Thanks very much.